Okay, so I think this was 10 minutes, so it's 5:30 here. As you can see, there's the dark February evenings of Berlin behind me during my window already, as we're approaching later hours here. So back to some conceptual overview. So the visualization tools Emanuela just showed you are really to understand your data and what's going on there. I think it's worth spending some time on this if you attempt to do sequence analysis. And also, even if you're doing, I don't know, an event history analysis or so on, you might also be interested in just the longer process that your central transition is embedded in. Those are, consider them general visualization tools to understand categorical longitudinal data. But this is, of course, more sort of the descriptive part, although you do see that things like selecting colors or how to reduce complexity in the graphs and so on is a concern here and a bit more sophisticated than your usual bar chart. But we're not at the actual analysis part yet so much. And that's what we're going to move to more. First with me again with the conceptual part, and then Emanuela will take over again, first showing you how it will look like in R, and then we will continue with the script and the data that we provided. So what I'm going to talk about now are first two very basic different ways of analyzing these sequences. The first one is looking at within sequence variation. So here we have the complexity measure as a prominent one, but there are many other summary measures. But the point is here I am somehow trying to summarize the structure, how many transitions, how much do durations in different states vary, how precarious or unstable is this individual sequence. And we come up with one value for each individual sequence. And then these values can easily be used, for example, as dependent variables in a regression model. The other way of analyzing sequences, and this is what we have to do to, in the end, get to a typology, is looking at between sequence dissimilarity. So to find two group sequences that are similar or that are different, we focus on between sequence differences, and here the most prominent method is optimal matching, but there are others, but we will only focus on optimal matching today. And once we have this pairwise distance matrix that optimal matching gives us, we need to apply cluster analysis to actually come up with these typologies, as I showed you in the beginning. So we will hopefully give you enough information to sensibly apply cluster analysis in the context of sequence analysis without being able to go into much detail here, which of course is a big field of its own. But let's first start with the first way, where we're looking at variation, the temporal structure within sequences. So here we have to distinguish between two types of summary measures. The first one are unvalued, and the second one are valued summary measures. What do I mean by unvalued? Here we are only looking at the temporal structure. So that's something like counting the number of transitions. I don't care if it's upward mobility or downward mobility, if the transitions are between being divorced and married or cohabiting and married. It's simply looking at the number of transitions and variation in the duration. And so these measures can be informative, but there has been a lot of critique, especially in the field of labor market research, when then I come up with also, this is a very complex employment sequence, labor market career, but one of them constantly switches between unemployment and a precarious job, whereas the other one constantly moves up the career ladder. There's a lot of temporal variation in both of these sequences, but in one situation we have socially undesirable states, and in the other one we have socially desirable states. So more recently, some new measures have been developed that value the transitions and the states that occur in the sequences by their social desirability. Now, whether a state is socially desirable or not, or should be valued positively or negatively in your specific application is, of course, purely a theoretical question that you will have to decide on your own, where no method can solve for you. So some prominent ones of the valued ones are so-called degradation index, where you compare the proportion of positive to negative changes in the sequence. So in the stratification sense, you can think of this of net mobility in a work career. Then there's a so-called badness index where you can weight each state that occurs in a sequence by the degree of undesirableness. For example, you could say being unemployed is bad, but at least you're still receiving benefits. Being out of the labor force and out of benefits with no entitlement to any benefits is even worse. So I will weight that more negatively and so on. So this is what you can do with this index. Then there's a so-called insecurity index that takes into account number of transitions, proportion of positive to negative changes, and degree of undesirableness. But you can also look at, for example, the probability to end up in a positive state at the end of the sequence. So there are really very many options. And there's an excellent recent paper by Gilbert Richard, who is also very important, leading the group that developed TRAMINA. He just retired, a statistician from the University of Geneva, who was always very open and committed to understanding the theoretical motivations of us social scientists, and is really a very central figure in developing the R package and a lot of the new measures. And he has a new paper out measuring the nature of individual sequences, because here we're looking at these temporal structures within individual sequences. And he discusses very many different ones. Here you just see an overview table of a lot of the measures that are all available to easily to calculate in TRAMINA and TRAMINA extras. So here in this sense, calculating them in R is really simple. Understanding what they are actually doing and specifying the input is another thing. For that, you of course have to look at this in detail. And Emanuela's and Marcel's Sage book, the forthcoming one she mentions, also has a very detailed explanation and hands-on examples to do this. So here, in the interest of time, I just want to show you what can be done or what kind of things you can learn, for example, by applying them. So here what we did is we used share data and from the Gender and Generation Survey data for many European countries and many different cohorts. So I think we have 20-something European countries and cohorts born from 1916 until 1966 to look whether family life course complexity has changed across cohorts and how it varies across countries. And here we had family life courses up to age 50 with my co-author Zachary Van Winkle. And so there's always this argument that family life has become so much more complex over time. But then empirically, this is not so clear. And one thing we show in this paper is that, yes, indeed, as you see here, this is the complexity index. So basically, the number of transitions in the sequence relative to the number of the theoretically possible transitions is what this measure is. But the result was that actually there is a slight increase in family life course complexity, but not even among the most recent cohorts. And the variation between European countries is much larger, and this is also stable over time. So also, if we want to study these differences, we might look more at cross-country differences than over time change. And this whole narrative of increasing complexity just as an unvalued increasing number of transitions isn't so clear. Part of this is because, of course, also childlessness increased, and we have a lot of sequences that have become where less things are happening in the family life, whereas in others more is happening. So we do see a polarization of this complexity within the countries, but on average, it hasn't increased so much. So this is something that even an unvalued complexity index could do for you to answer these types of questions. Then when we come to the valued summary measures, here I brought you an example of the badness and degradation indices, where we looked at work trajectories, so employment careers from age 20 to age 40 in Germany, and whether these predict political interest. I started this project with a political science colleague where we're looking at life courses and political behavior. And indeed, here we see, so this is the badness index in work lives and the degradation index. And here you see a dummy variable for high or low political interest at age 40. And indeed, we see people who have a very bad or downwardly mobile, badness might sound too normative here, downwardly mobile and precarious work career indeed have lower political interest at age 40 compared to those that are not downwardly mobile, which would also be in line with theory. So this would be another type of thing that you can do. They can be interesting, like in the complexity example, when you compare across countries and cohorts and have some kind of theory about structural factors that vary across countries and cohorts that create this complexity in the life course sequences. Or they can be interesting then if you're trying to predict an outcome to say, does it matter if you were upwardly or downwardly mobile, or what the structure was, how many transitions you had, and whether they, in which direction they went. This, which I think could also be quite interesting for health outcomes, where then of course you could compare controlling for general level or work situation at age 40. And then on top of it, does it matter if things were so volatile in the last 20 years? Okay, so this is just in the interest of time, we will give you some code. And as I said, they're all implemented in Termina, but to let you know that these, there is a sophisticated toolbox of indicators and individual sequence variability, the temporal structure here, and the kinds of questions one might address with them. Are there questions at this point that we should talk about? Okay, I see Emanuela shaking her head. Then let's move to the between sequence differences and creating typologies. So here, optimal matching, which, as I already mentioned, was originally developed in biology to analyze these strings of DNA. And by the way, also is used in, if you do a Google search, there's a type of optimal matching algorithm comparing the letters that you type into your search to letters on the internet. So search machines also use these types of algorithms. Has really become sort of the standard form of sequence analysis used in the social sciences. But there are others. It was originally developed by Vladimir Levenstein in 1965. And as I already said, for DNA and speech recognition algorithms. And then Andrew Abbott first introduced sequence analysis specifically with an optimal matching application with a paper actually in 1986 with a historian called Forrest, I think John Forrest, where they analyzed, it was a historical cultural sociology application, and they looked at the cultural diffusion of dance steps in the United Kingdom. So they're the Morris dances, and each village had sort of their own sequence of dance steps that made up the specific Morris dance of this village, and they were recorded in sort of village town hall books, whatnot. And then they could reconstruct how closely connected villages were over time, and how these specific sequences of dance steps diffused regionally. So I think it's interesting, this application, and there are some in cultural sociology, but of course it's a very different type of application than the fields that now 3 decades later, sequence analysis is most used in. Now, when we apply optimal matching, the goal of this whole procedure is to quantify the degree of similarity of sequence pairs. So we're comparing everybody to everybody else to then identify who is similar to each other and should be grouped in one cluster. And the way optimal matching approaches this is to find the quote unquote cheapest way to transform one sequence into the other. So this is a method of alignment where, to determine similarity, I ask, how many changes do I have to make to turn sequence A into sequence B? And let's say they are completely identical and only at the end they have 2 different states. I only need to make one change to turn sequence A into sequence B. But if they are very different, of course, I would have to change very many elements to turn one into the other. And this would then amount to a high so-called transformation cost. So the language used here is transforming one into the other. And for each operation of sort of replacement is attached a specific cost. And by varying these costs, what the researcher can do is emphasizing different features of similarity. But I'll talk about that more in the next couple of slides. So anyways, the output you get from this whole process is a pairwise distance matrix for all possible sequence pairs. So what am I going to do typically if I want to conduct optimal matching? First, I define my sequences, the start, the end, the alphabet of states, and this involves very many decisions, as you learned before, and then I visualize them and understand what's going on. Then I apply this optimal matching algorithm to assess the sequence similarity and get the distance matrix. And with this pairwise distance matrix, I can do all sorts of things. Either I put it into a cluster analysis to get a typology of trajectories, or I can use the distance matrix as a direct indicator for the differences, how standardized or destandardized, how much variability there is in one group of sequences as opposed to the others. And there's other ways also to analyze these distances. What you cannot do is use these distances easily as a dependent variable in a regression analysis. And the reason is that the units of analysis here are pairs. So we get one value for each pair of individuals, and we don't have just one value for each individual, like with the individual sequence measures. So this would be a distance matrix for 4 sequences. So you see here the diagonal always are zeros because that's comparing sequence 1 to itself, sequence 1. So of course they are identical and the distance or the dissimilarity is 0. And then here I see, for example, sequence 2 to sequence 1 only has a dissimilarity of 1, but sequence 3 to sequence 1 has a dissimilarity of 5. So I know that 3 and 1 are much more different from each other than 2 and 1. And so maybe likely 2 and 1 will be grouped into the same cluster, but 3 and 1 will be grouped into different clusters. Now, how does optimal matching actually calculate these distances? As I said, the logic is to find the cheapest way to transform one into the other. And for this, optimal matching uses 3 so-called transformation operations. So there are 3 things I can do to make one sequence more similar to the other. The first one is I substitute one state with another. That's basically replacement. Let's say I have 2 completely identical family formation sequences. Just one person at the end gets married while the other stays single. I simply replace this being married by being single, and then they are identical or the other way around. But that's a substitution operation, a so-called one. And then what I can also do is inserting or deleting a state. And this becomes important. For example, let's say you have 2 sequences that are exactly identical, except in one sequence, everything happens a little bit later. So here, to make them identical, if I would substitute all the time, I would need very many substitutions. But if I just pull out, delete one state in the beginning and the whole thing shifts to the back a little bit, then they are already identical because they had actually the same order, just a slight shift in the timing. So this would be inserting or deleting a sequence. Here I brought you an example of aligning 2 sequences. Let's say I have 2 very simple sequences here, employment, labor market sequences. At time 1, first person is unemployed, then in an internship, then 2 time periods of employment. The other person is in education, then unemployed, then employed, and has a shorter sequence. And I would say substitutions cost 2 and insertions or deletions cost 1. Then here, to turn sequence 1 into sequence 2, I would substitute unemployed for education, internship for unemployment, and here I would insert another employment, and this would add up to a cost of 5. Now, what optimal matching does, usually there are many different ways to transform one sequence into another. And what the algorithm does is it walks through all possible ways of transforming one into the other and then selects the cheapest. But this is why it's so computationally intensive, because first of all, I'm comparing everybody to everybody else. So I have a larger number of distances and comparisons than I have individuals in the sample. And then the algorithm has to walk through all possibilities of transforming one into the other to find the cheapest way of doing this. Now, the crucial issue here of cost specification. Now, when I do an insertion deletion, what is preserved are the events, and what is altered is the time. When I do a substitution, I'm preserving time and I'm altering the event. And as a result of this, let's say I want to emphasize similarity in terms of timing. I'm a family demographer, and I know it really matters when family formation starts, whether it's at 15, 16, 22, or 24. And I want to make sure that only those two sequences are considered similar, where the same things happen at the same time. What I'm going to do then is I'm going to have really high insertion deletion costs and really low substitution costs, because then the algorithm is going to use these substitution operations that preserve time and alter the event. So because this is going to help me to identify people as similar, where exactly the same things happen at exactly the same time. Now, let's say I'm a labor market sociologist, and I don't really care how long it takes somebody to be upwardly or downwardly mobile. I only want to know the order of the states. I want to know, are they shifting frequently, and is this moving up or down? And I don't care if this happens in 10 or 20 years. Then I want to emphasize similarity in terms of the order of states. And to do this, I will specify low index costs and really high substitution costs, because then the algorithm is going to identify individuals as similar who experience the same states in the same order, regardless if it's at exactly the same time or not. So you have some look into this into detail and think about what you actually want to find if you're thinking about applying this. The crucial point is you have some leverage here as to which aspect of the sequences you want to emphasize when you identify how similar they are to each other. And this should be guided by your theoretical ideas. Now, here's a quote by this paper, and that's another nice paper by Kate Stovall, Savage, and Berman, one of the early ones, Ascription into Achievement, Models of Career System at Lloyds Banks, also historical sociology, next to Kate Stovall's very nice lynching paper, also from around these years. And this was the point when there was a lot of debate early in the sequence analysis field, where some people, Abbott was really promoting it very heavily, and some people were not convinced at all. And this one of the core criticisms was these transformation costs are completely arbitrary, and you just make up something and then something results, but you cannot really validate if this is statistically sound. And so here, one of their quotes was, "The assignment of transformation costs haunts all optimal matching analysis." And in the early papers, you see that people go through great length to justify their costs and try to link them to theory and make up specific substitution costs, that substituting to some states is more expensive than others, and how this can be justified and so on. And I would say now, in hindsight, cost specifications do matter, and you have a very wide variety that you can choose, but many of them actually produce similar results, because if you have main patterns, core types in the data, you will usually find them pretty similar with several different cost specifications. And what we also know in the meanwhile is that the results are often more sensitive to how exactly you specify your alphabet and which clustering procedure you use. But reviewers usually want to see, of course, a justification. You say, I'm interested, timing is really central. That's why I'm setting low substitution costs, or I'm using another measure. There are various that emphasizes timing. And then it's also advisable to run some robustness checks. But I think the more applications we have seen, the more this has become sort of not a ghost unvalidating the method, but simply a choice where you have sensible options and should do some robustness checks. And again, here, there's by Matthias Studer, also a member of the Geneva team, who also is programmed the weighted cluster package, the clustering for sequence analysis, and was also one of the really major figures in the Traminer group. They have a 2016 paper, What Matters in Differences Between Life Trajectories, a comparative review of sequence dissimilarity measures. And this has become sort of the go-to reference where you say, for this and that reason, I choose this dissimilarity measure. Because what they did is, again, a very wide variety of existing ones. They tested them in a simulation study as to how sensitive they actually are to picking up similarity in terms of duration versus timing, or sequencing, so the order of states versus timing and temporality. And based on these simulation results, they placed all these distant measures here in this in this space, and then you can say ground your choice of a distance measure very nicely, for example, by referring to this great simulation study that shows us what they actually do. Okay, other questions to optimal matching that couldn't be solved in the chat?
One popped out now. How much means high and low cost?
High and low cost. Yeah, so high and low cost, good point. Never matters in an absolute sense, but in a relative sense. So the thing why they matter is depending on how costly insertion deletion operations are relative to substitution operations, the algorithm will use more insertion deletion operations than substitutions. And this will lead to a different calculation of dissimilarity than when very many substitutions are used. So in an absolute sense, it doesn't matter. There's a handbook chapter from 2004 by Andrew Abbott and Heather McIndoe, and they suggest that usually setting insertion deletion costs at about half of the maximum substitution cost or half of the substitution costs ensures that both the timing and the order of states are taken into account when looking at, when determining the dissimilarity. So this is often cited to justify this cost specification when you want both the order and timing to matter. But then there are also options. I just see there's a question. This is in the chat. That's perfect. What is if you take transition rates? This is another thing you can do, that you say substitutions between two states where the transition rates are very high. So where transitions occur frequently should be cheap. But this is this sounds reasonable, but when you think about it, it isn't necessarily, because very many people transition from education into having a job. So that's a very frequent transition, but that doesn't mean that being in education and having a job is actually a similar state in a substantive sense. So this has been used, and in some applications, I think it makes total sense, but in other, it also has been criticized. And my experience is using simple optimal matching or the transition rates doesn't make a huge difference. Usually the clusters are extremely similar. But there are also others where you only use substitutions or the dynamic Hamming substitutions and transition rates. So there are many different options here. And depending on what you want to show, they can be reasonable. Okay, more questions? Then, Emanuela, I'll pass on to you with the clustering, or should I start and you take over?
No, I can take over. Just I share my slide.
Yeah, that's probably better.
All right. All right, so we now know how to, let's say, attach a number to the dissimilarity between sequences in our set of sequences. What do we do with that? Well, most of sequence analysis applications apply cluster analysis to the dissimilarity matrix, to the pairwise dissimilarity matrix that we just learn how to generate. Cluster analysis in this sense has several objectives in this context. First of all is to partition the sequences into groups, but those groups ideally are as similar to each other, the sequences in the groups are as similar to each other as possible and as dissimilar to sequences in other groups as possible. So we have to maximize the within cluster similarity and the between cluster dissimilarity. The point of this procedure is to simplify the complex data we have. So as in the very first example, we can visualize two sequences. It's much harder to make comparison across 1,000 sequences. We can identify similarities between two sequences, but it's hard to quantify the dissimilarities between many sequences. So we need to simplify this complex information, and cluster analysis is a way to do that. Of course, every simplification comes with a cost, and the cost here is that we have to ignore minor differences between the sequences that are located in the same cluster. So we want to generate a meaningful typology of sequences, and within this typology, each cluster, so each type, will have a certain amount of differences, but we have to ignore it. So we accept that this is a minor difference that we assume can be ignored. This might lead, though, to ignoring major differences and lead us to false substantive conclusions about the typology. How can we be sure that this is not happening? Well, there are some heuristics we can use, but most importantly, we need to know our data very well. And that's why all those steps that we have discussed so far, the visualization, looking at the transition rates, looking at the frequency of specific state across groups, etc., can support us along the process. So the main question we want to address here is which are the typical trajectories existing in my data, with the assumption that we can ignore minor differences at the cost, taking the risk of ignoring some major differences. We will decrease this risk via a certain number of heuristics, but we have to keep this in mind very firmly. So this is also important because we can do things with the typology we extract from the data. For example, we can wonder why are given ideal types in the data. So we can link the different types to different generating institutions, so to different historical circumstances. So for example, are family formation processes in familistic welfare states different from family formation processes in less conservative welfare states? This would be to link the a specific type of trajectories to the characteristics of the institutional context where those sequences unfold, so those processes unfold. But we can also wonder who are in the population more likely to experience a certain life course. And here one might want to explore differences by race, gender, social class, education, etc. So how is the unfolding of a specific trajectory linked to the fact that individuals have different baseline characteristics? But also we might want to know something about the consequences of experiencing a certain life course or a certain temporal process more generally. So for example, we want to know whether working part-time for the whole life course might lead to lower pension and higher risk of old age poverty. Is this something that happens specifically to women or to men? So we want to link the configuration of specific trajectories to something that happens at the end of the observational period we consider here. So you can see here that we can use clusters as predictors of something, pension at later age, or as outcome of something, individual characteristics, institutional or historical circumstances. In the field of cluster of sequence analysis, there are two major families of clustering algorithms that are used: hierarchical methods and partitioning around centers. Hierarchical methods are typically either bottom up or top down, and partitioning around centers are the so-called k-means or partitioning around midways. So Also, in this case, if you use other softwares that are not R, you might want to explore further options. But in most applications, some hierarchical clustering relies on Ward's algorithm, and the partitioning around centers generally refers to partitioning around metrics. As I said, Ward is the most commonly used, but the package that is used for most applications is H-class in R. And as you see, H-class actually allows for many different types of clustering algorithms. All are pros and cons. The most widely used is this Ward. The reason is that minimizing the residual variance, and this is something desirable in this kind of procedure for our cases, given that we want to keep the differences within the group as small as possible. How do we do that in R? So you should be right now a little bit more familiar with the standard language we are using here. We generate objects using this flag, and we put into those objects something that comes out of a function. And the function here is this H-class. And we have to specify the distance matrix, which we generate within Traminer, and I will show you in the hands-on how to do that. For now, it's useful to know that this distance matrix is a pairwise distance matrix that we call here OM after optimum matching sum. And we have to specify the method. And here is the word linkage, as I said before, which gives us a hierarchical, a hierarchical cluster. And here we can further specify the weights using the members option. Keep in mind what we said before about weighting. What we can use this object we generated with the H-cluster function for is, most importantly, to see how the data are clustered after we apply this algorithm to our set of sequences. And one way to explore this is to use the dendrogram. The dendrogram can be easily plotted using the plot function and plugging in the object we generated with the H-class. And here you see that this black bar here is actually not a bar, but are individual sequences in our data. And these are very packed and very close one to another, so we cannot really distinguish them. But as we go up on the y-axis, we see that there are some links between groups of sequences that generates clusterization that progressively goes up to a certain threshold where the dissimilarity is very large. What happens if we decide to extract two clusters out of this? Well, we have to kind of set a line here to cut two of these branches. And we say everything that is below this branch belongs to one cluster, and everything else that is below this other branch belongs to another cluster. As we go down and we cut more of these branches, we can cut out more clusters. What happens to more clusters is that the within cluster dissimilarity will decrease according to what it says on the y-axis. But how many clusters then? So is it sufficient to look at this kind of dry figure here to decide what is meaningful for us? What are the types that are meaningful for our research question? Well, is not sufficient. So we can have an idea about what happens there, but a visual inspection of something else other than the dendrogram is necessary. The first thing we want to consider is other criteria that are called cutoff indicators. Also, in this case, Traminer allows you to explore many of them. You see a compound list on this slide. I would say that 95% of the papers rely mostly on this average silhouette width. This is an indicator that gives us a sense of the coherence of the assignment of each sequence to the cluster. The value itself goes from -1 to 1, so that each each sequence will be given one value of this indicator. And the higher the value, the higher the coherence of that sequence to the cluster that the clustering procedure has assigned it to. So what we want to maximize, of course, is not the individual silhouette to the cluster, but the average silhouette width of all sequences assigned to a specific cluster to that cluster. How do we calculate that? Well, Trauminer gives you help with that. The s.clustrange function, when you use hierarchical clustering, you see here the input is the output of the h-class function. We specify the dissimilarity matrix. And again, you can specify weights if you want. And here I want to know for at least 7 clusters how those values look like. I store the results of this into an object that then I can print. And here the return is the values of all the quality cluster criteria that were presented in the previous slide that I couldn't really go through, but let's focus on the ASW. For different clustering solutions, so for 2, 3, 4, 5, 6, 7 cluster solutions. What we see here is that there is a small peak in this value around the cluster 4 and cluster 5. This peak actually is stable when we move from cluster 4 to cluster 5. It means that according to this criterion, it's the same to extract 4 or 5 clusters in terms of coherence, average coherence of the sequences to the cluster. So now we are again to the previous question. So how do we choose at least between 4 and 5 clusters? Well, here visualization is what we need. Visualization together with a strict focus on our research question. Before moving to that, I want just to show you that besides looking at the table, you can also plot those values across number of clusters. You see the code is not very complex. You can manipulate many things, show actual values or z-scores, etc. But the values are the same as those in the table, of course. Okay, so we can first visualization can help us displaying the silhouette itself for all the sequences. So we want to identify whether some clusters are really bad or whether some are really strong in terms of within cluster coherence. We use the silhouette function, the object that we generated with the h-class, and again, specify the dissimilarity matrix. And we get first a summary, and then we can use this object that we generated, this sil word. We can plot it and look specifically at what happens in the cluster. So here we see that 1, 2, 3, 4 clusters are extracted. And we see that for the first cluster here on the top, which is also the larger, because you see that many sequences, which here are basically horizontal lines, one next to the other. Many sequences have positive values. Here on the x-axis, you see values above the 0. Only a few have values lower than 0. It means that only a few are not really coherent with the cluster. This is a relatively strong cluster. In fact, when we look at cluster 3, we see that a much larger share is actually displaying negative values. It means that when we will look at this cluster, we might wonder about how homogeneous it is. So how this type is actually telling something about similar individuals or not. So remember the trade-off we discussed before. For some of this cluster, cluster 1, cluster 4, we can be pretty sure that we can ignore minor differences. Maybe for cluster 3 is less so. So I recommend always to look at this silhouette plot because it helps you grounding the understanding of the clusters and how strongly you can rely on the substantive interpretation. Okay, but this is only one type of visualization we can use. Before moving to actually visualize the clusters, some words about the evaluation of cluster quality. As I mentioned before, cluster analysis simplifies the data. Might be meaningful or not what we get, basically because the cluster analysis always produces a result. And this means that the types will always be extracted in the number that you decide. Whether those types make sense is an empirical question and need to be evaluated looking at the silhouette as we just did, but also looking at different clustering options from like a cluster-based point of view. Being this a descriptive technique, it's hard to give you rules that actually validate your typology in a strictly statistical sense. Here we are more in this domain of construct validity. So we have to basically find validation criterion or a heuristic that support us in interpreting the data one way or the other. Remember that a good typology should be generalizable to other observations. So in case you have different data sources for the same cohorts or the same process, it's a good idea to test your typology across different data. Should be generalizable to other properties. So it's important to look at the link between individual characteristics, for example, and the process. So do they make sense? And link to a theory. So it's important that before approaching your data, although this is a descriptive technique and in many cases is used as kind of a heuristic for how the process looks like, you have to have an idea of how you expect those clusters to look like. So, and whether it's important for you to identify clusters that emphasize specific aspects of the process. Therefore, generalization can be done with a grain of salt, especially, well, not especially, but it's very important that you are knowledgeable about all the steps, all the decisions you make, starting from the decision of the states that you use to codify your sequences, the decision of the dissimilarity matrix, so the cost that you use for the optimal matching, and the procedure that you use for clustering them. All right, this is basically what we just said. You can explore further extension of this setting, but maybe here, Annette, you wanted to take
Yeah.
I leave you the slide and I go on to you.
Great, thanks, Emanuela. I'm just answering one more question by Yoon on what can I do with a group that has very low silhouette widths, which is sort of a bad cluster. So here I would say that for descriptive purposes, we can just simply describe this. This can be interesting. For example, I did an analysis of retirement trajectories comparing Germany and the UK ones. And my clusters were pretty crystal crisp and clear in Germany, because I have a very strong welfare state here that very strongly structures lives. And in the UK, a more liberal welfare states, my clusters were all fuzzy and rough around the edges, much worse cluster quality. But here this made sense because the liberal welfare state simply doesn't group lives to the same, doesn't shape and group lives to the same extent as the German one. So this can be a substantively interesting feature. And if it's just about describing or comparing on this level, I would simply document it. But where it becomes, of course, very important is if you want to use these clusters as dependent or independent variables in a regression model. And here, if you have very heterogeneous groups, that's a problem, because the coefficients then that you get for this typology, then they probably will be weak and spurious. So what you can do here, and what has been starting to be done in recent applications, is that you exclude individuals with low silhouettes for regression analysis. So you can get for each individual case how strongly they reflect their cluster. And then you can say, first I describe my typology, and these are the fuzzy ones, and these are the crisp ones. But then I move to the second part of the analysis where I want to use them as explanatory or as outcomes. And here I just drop all cases that have negative silhouettes. And then I simply have to document this and say my regression analysis is only for pure types. And then I think it's fine. So because here what you have if you keep all of these bad silhouettes is classification error in the clusters. But I wouldn't think about it as a data problem. It's basically a substantive fact about how these lives in this case are structured. So it's a result rather that you have to deal, that you can display and work with rather than a problem. Okay, so coming to
maybe can I add something to this? We'll maybe see this when testing for different cluster options and comparing the visualization for that. Here we extracted for cluster in the example. As we have seen before, the ASW values were the same for also the 5 cluster solution. It can also be the case that those that are misassigned to that cluster in the 4 cluster solution will be reallocated, like taken as a package and reallocated to the new cluster if we extract 5 clusters. So that's also important when you choose the number of clusters to see what happens when you change the number of clusters extracted, because maybe those that are not well allocated in one partitioning will be reallocated in a better way in the next partitioning and actually generate an interesting, substantively interesting new type. So that can also be the case. Then what I meant to said stands, but as a step before, when you decide about the number of clusters, you really have to inspect, as we will see in the hands-on, how this cluster look like. And maybe when you extract 1 cluster more, this will highlight a new type that is solving the misallocation problem.
Mm-hmm. Yeah, excellent. Thanks, Emanuela. So we're almost done here with our slides. I think we have 99, or just short of 100. But what we try to do now is give you sort of a basic idea of where sequence analysis came from into the social sciences, what's the theoretical motivation here, and on a basic level, what kinds of things it can accomplish for you and get you sort of set up that you can start running it. But especially in recent years, there are many sort of further developments based on what we looked at now. So there was a question earlier already in the chat, what do I do if I have parallel processes? Here you can use multi-channel sequence analysis that helps you identify. It also creates a distance matrix and helps you identify individuals that are similar and have similar health trajectories and similar labor market trajectories and similar family trajectories maybe. This can be done. There's a lot happening at the moment in the field of visualization, and then a lot of combinations with other methods to overcome some of the limitations. So I think these are actually quite interesting. For example, with Emanuela and Matthias, we have a paper where we combine event history models with sequence analysis, because if you think about these clusters, they summarize a temporal dynamic, but they all start at the same time and end at the same time. And for example, you cannot estimate the impact of a time varying covariate on cluster membership easily. But with the sequence analysis multi-state model, we found a way on how you can also estimate how time varying covariates affect the probability to then experience a certain trajectory rather than just a transition. And then also with the Bayesian information criterion and likelihood ratio test for sequence comparison with Tim Liao, here we tried to adapt these big and LRT criteria using sequence distances similar to errors in regression models to put a number on the degree of difference and also significance levels on how different 2 sets of sequences are. Let's say you don't want to cluster, you simply want to know how different are the life courses of women born 1980 compared to women born 1960. Then you could use these types of methods as well. So there are quite a bit of things going on and extensions here. Now, in the beginning, when we started, thanks. Oh, can you go on? Yeah, that's there. We have the full figure. Thanks a lot. So in the beginning, I showed you these family life courses from the NLSY data. And this is actually part of an analysis that was a multi-channel sequence analysis where we tried to look for similarity in both employment and family life courses. And the dark red here up in the work trajectories are high prestige occupations, so high earning, high prestige occupations. And the yellow are low prestige, low paying occupations. And then you see this purple and black here. So these are employment interruptions. And so here we see in the US, we have this group down here that where we have a very strong connection between this early single parenthood and enduringly precarious low income careers. So until age 44, once people are on this track, there doesn't seem to be much moving out up until age 44. And we have all these precarious work careers, whereas we see sort of the normative traditional family life at the top combined with the high stakes careers. And what we did then, so to just show you what this type of analysis would look like, is we were interested sort of in an intersectional perspective, how the probability for Black men and women would vary to be in these different life course types. And what we saw, so here you see these life course types, they were then a dependent variable in a logistic regression. Up here, group 7 is the one with the highest income. Group 1 down here has the lowest income, single parents with these very disrupted careers. And then you see predicted probabilities for Black men, Black women, and white women to be in these groups relative to white men. And we saw indeed that Black men had a higher probability by almost 25% to be in this lowest income life course, and also a significantly lower probability to be in the highest income life course. But it was much worse for Black women. So their probability to be in the lowest income single parent life course was almost 35%. And also the probability to be in the highest paying one was more than twice as reduced compared to Black men. So here indeed we found some intersectional differences. For white women, the effects are much smaller and they have basically equal likelihoods to being in the highest paying group than white men, but we do see some elevated likelihoods to be in the lowest paying group. Emanuela, if you can go back to the clusters. Yeah, but the idea here is that what we're looking at is sort of a process outcome of inequality. You can think of it as a distribution of life courses, also a life cost stratification, where instead of looking at an income distribution in a given calendar year, we're looking at how really these lives of 20 years of the life course are distributed in the United States for these cohorts, and then whose probability was greatest to experience the more or less economically rewarded work and family lives. So just kind of to close the frame and give you an outlook of where we start with a big pile of chaotic temporal sequences, then we try to order them into coherent groups, and then to make sense of the groups by connecting them to other pieces of information. And this, I think, is the end of our conceptual part. All of the slides and so on will be online, and of course, feel free to email us. We have, we're happy to take questions now. We also have half an hour left. I would suggest we can take questions first, and then there can be a short break. And those of you who want can then stay, and we will use the last 20 minutes, 25 minutes to walk you through the code for the optimal matching and clustering in R. So are there questions?
There was a question about whether you have a reference for papers doing what you suggested before to run a regression analysis excluding.
Yes, Marika and I did that in a recent paper. I will post it in the chat in a minute.
There's also
I just posted the paper with Marika where we do this with the silhouettes. So what we can also do here is you can sort the sequences by their silhouette value in, for example, one of these sequence index plots, and then you can see exactly what the ones that are well classified look like, as opposed to the more outlier sequences. And in this paper especially, it has a methodological appendix where we spend, I don't know, 5 to 10 pages on explaining these why and how to exclude those silhouettes. So you might want to, if you're interested in this specifically, then consult the appendix. Okay,
Okay.
then let's take a 5 minute break, and then we'll be back with the code.